This is a video on molecular and covalent network solids as well as p-type and n-type semiconductors. Let's start with molecular solids. This type of solid is made up of atoms or molecules that are held together by intermolecular forces, usually London dispersion, dipole-dipole, or hydrogen bond. Most substances that are gases or liquids at room temperature form molecular solids at low temperatures. Some properties include being fairly soft due to weak intermolecular forces, a low to moderately high melting point, usually below 200 degrees Celsius, and they are usually poor thermal and electrical conductors. It's also important to note that these properties depend on two factors. First, the strengths of forces that hold the molecules together, and second, the ability of those molecules to orientate correctly in three dimensions. Some examples of molecular solids would include argon, methane, sucrose, and dry ice. So to draw a molecular solid, we'll follow these steps. First, draw two molecules of the substance. And then second, you'll connect the two molecules using an intermolecular force. And third, just repeat the steps 1 and 2 to form a cube arrangement of the molecules. So for example, we'll draw ice. So first we draw two water molecules, remembering that O goes in the middle and then there's two smaller H's on the sides. And then we also have to keep in mind that when we draw them, we have to orientate them correctly so that O and H can form a IMF. So to form a solid of those two then, we would just continue layering them to make a cube arrangement. So next we have network covalent solids. This type of solid is made up of atoms connected in a network or chain of covalent bonds. Some properties include being very hard and having a high melting point due to the strong covalent bonds, and they're also generally poor thermal and electrical conductors, however there are some exceptions. So two examples of network covalent solids that show slightly different properties are two types of carbon allotropes. We have diamond and graphite shown here. Diamond is formed by one carbon bonded to 4 other carbons, so therefore all the bonds are strong single ones, which causes the unusual hardness and extremely high melting point. And on the contrary, graphite is formed by hexagonal rings that are connected by weak IMFs, and so due to this there are delocalized electrons around the layers, which makes it a good conductor. Also, it is much weaker because the layers slide off of each other, and that's how we can write with it using our pencils. So to draw a network covalent solid, we'll follow these steps. First, we draw a nonmetal that will form covalent bonds with other nonmetals, and usually this will be carbon or silicon because it has 4 valence electrons, so it can form bonds with other elements. And then second, we'll draw nonmetals bonded to the carbon and silicon to form a group of covalent bonds, and then we just repeat steps 1 and 2 to form a solid or chain. So for example, we'll draw quartz, which is SiO2. So we start off by drawing the silicon, and then we bond oxygens to that, and due to the repeating lattice structure, we bond 4 oxygens to 1 silicon, so it'll look something like that. And then you just layer it and put more silicons around the oxygens and more oxygens around the silicons. So let's do a practice problem. Which of the following is a covalent solid? Sulfur trioxide, nickel, ammonium chloride, silicon carbide, or sucrose? We can determine this by looking at the properties of a network covalent solid. We learned earlier that a network covalent is hard and has a high melting point, which are both due to the strength of covalent bonds. We also know that carbon or silicon are generally used as central atoms in a covalent solid. So because of those facts, we know that silicon carbide is the only one that's listed here that's able to fit the description because it forms both covalent bonds to produce a strong solid, and it has silicon as a central atom. So now it's time for you to try one on your own. So we're going to ask you to draw the molecular solid of methane, which is CH4, and then you can pause the video and resume it when you wish to check your answers. So this is what the solid should look like that you drew. You can see that there's 1 carbon surrounded by 4 hydrogens, and then the hydrogens form IMFs between them. Now the second half of this video is on semiconductors. In order to be a conductor, an atom must be surrounded by carbon or silicon atoms because they have 4 bonding sites. Some properties of the semiconductor would include being a variable conductor because of electron flow, producing light emissions, and having thermal energy conversion. There are 2 main types of conductors, and the first is an N-type. In this case, there is 1 extra electron, and this will cause a slightly negative charge. To ensure there is 1 extra electron, an element needs to be used that has 5 valence electrons, so anything from the nitrogen column. This is also an easy way to remember the N-type has 1 more because N equals nitrogen for the nitrogen column. So to draw this type of semiconductor, we pick an element from column 5 on the periodic table, and in this case we will use phosphorus. So So we're going to start by drawing the Lewis structure, which is shown on the screen. So it'll be a P surrounded by 5 valence electrons. And then we'll take 4 silicon or carbon atoms and place them around. So in this case, we'll use silicon. And then we'll draw the Lewis structures of the silicon atoms around the phosphorus. And as you can see, since the silicon only has 4 bonding sites, we can only bond 4 silicons to the phosphorus, which means that we'll have 1 extra valence electron around the phosphorus, which creates the N-type semiconductor. Now the second type of semiconductor is the P-type. And in this case, there's 1 less electron, which causes a slightly positive charge. So to produce a hole in the graph, we pick an element from column 3 because they only have 3 valence electrons, not 4. And a way to remember that the P-type has a hole is that the letter P has a hole in the middle. So to draw this type of semiconductor, we pick an element from column 3, and in this case, we'll use boron. So we again start by drawing the Lewis structure. So boron has 3 valence electrons around the outside, and then we'll take 4 silicon or carbon, and in this case you can see silicon, and we'll place them around the boron atom. Now we can again place 4 around because of the 4 valence electrons that silicon has, but then you'll notice that around one of them there's a hole. So now it's your turn. First, draw an N-type semiconductor using nitrogen and silicon, and then draw a P-type semiconductor using aluminum and carbon. And then you can again pause the video and complete the problem, and then resume it when completed. So this should be how the 2 semiconductors you drew look. The first one should have an N in the middle for nitrogen, and then it should have 5 valence electrons around, and then 4 silicons, and then you can see that there will be an extra valence electron around the N. And then the second one should be aluminum, and you should see that there's a hole produced because aluminum only has 3 valence electrons. So now let's do a quick review. So first we have molecular solids, which are held together by IMFs. They're soft. They have an average melting point, and they are poor thermal conductors. Network covalent solids are held together by covalent bonds. They're hard, they have a high melting point, and are generally poor conductors. An N-type semiconductor has an extra valence electron. It uses elements from column 5 plus a carbon or silicon, and it also is N for nitrogen, to remember that. And then the last is the P-type semiconductor. It has 1 less electron. It uses elements from column 3 plus a carbon or silicon, and you can remember that it's P for a hole. Thanks for watching.